Right now, roughly half of every human being alive exists because of a single chemical reaction discovered in a German laboratory in 1909. Not a medicine, not a weapon, not a technology. A reaction that turns air into food, literally. But before we get to the miracle, we need to understand the catastrophe it was racing to prevent. By the late 1800s, the world's population was exploding. Europe alone had doubled in a century, and every extra mouth needed food. Plants need nitrogen to grow, and farmers had exactly two sources: bird droppings and bot guano shipped from remote Pacific islands. Guano became so valuable that nations went to war over it. The United States passed a law claiming any guano island in the world as American territory. When the guano ran low, the world turned to Chilean saltpeter, vast mineral deposits in South America. But scientists did the math. Those deposits were running out too. In 1898, the chemist William Crookes stood before the British science establishment and issued a warning. Within a generation, billions would starve. The irony was suffocating. The atmosphere above every farm is 78% nitrogen, but plants cannot use it. It just floats there, useless. Somewhere in Germany, a young chemist with round glasses and relentless ambition heard that challenge. His name was Fritz Haber, and he had an idea. Haber was not content to simply admire the problem. He wanted to own it, to crack it open and find what was hiding inside. The air around us is nearly 4/5 nitrogen. It is everywhere, in every breath, pressing on every surface. Yet for all its abundance, it might as well be a locked vault. Two nitrogen atoms bond to each other with a triple bond, one of the strongest links in all of chemistry. Breaking it demands enormous energy and conditions nearly impossible to create. Nature found two narrow pathways through that wall. Lightning rips nitrogen apart in a flash, forcing it to combine with oxygen. And certain soil bacteria do the same trick, slowly and quietly underground. But these natural routes were a trickle compared to what a world of 1.5 billion hungry people needed. Farmers were running out of fertilizer and running out of time. Chemists across Europe knew the answer was floating right above their heads. Fix nitrogen from the air at industrial scale and you could feed the world. The prize was obvious. The method was not. Every protein in every living body contains nitrogen. Without reactive nitrogen, there are no amino acids, no enzymes, no muscle, no thought. Life itself runs on a supply that nature could barely produce fast enough. Haber understood this better than most. He had already spent years failing at smaller chemical problems, and every failure had sharpened him. Rejection only made him more stubborn. He set his sights on the triple bond, on the locked vault in the sky. If pressure and heat and the right catalyst could force nitrogen and hydrogen together, ammonia would come out the other side. Simple in theory, ferocious in practice. Haber knew the theory. Nitrogen and hydrogen, forced together under the right conditions, would yield ammonia. But knowing and doing are separated by a vast and dangerous gulf. He started with heat, lots of it. High temperatures give molecules the energy to collide with enough force to break bonds, but heat alone just made the reaction run backward. Ammonia is unstable at high temperatures. Push the heat up, and it just breaks back apart. Haber needed pressure to tip the scales, to crush the molecules together so tightly they had no choice but to bond. But even heat and pressure were not enough. The reaction was too slow to be useful. Haber needed a catalyst, a substance that would speed everything up without being consumed itself. He landed on osmium, one of the rarest and most expensive metals on Earth. Exotic, almost absurdly scarce. But it worked. In 1909, in his Karlsruhe lab, ammonia dripped out for the first time. It was a tabletop miracle. A few drops of ammonia from thin air. But the world did not need a few drops. It needed mountains. That was someone else's problem now. That someone was Carl Bosch, a hulking, brilliant engineer at BASF. When Haber showed him the tabletop reactor, Bosch saw not a curiosity, but a civilizational lever, and he decided to pull it. The engineering challenge was almost incomprehensible. To produce ammonia at industrial scale, you needed reactors running at 200 atmospheres of pressure. That is 200 times the weight of the entire sky pressing on every inch of steel. The early reactors kept exploding. Hydrogen at extreme pressure has a vicious trick. It seeps into steel and makes it brittle. Then the whole vessel shatters. Bosch's team called it hydrogen embrittlement, and it was killing their machines. Bosch solved it by lining the steel vessels with soft iron, letting hydrogen seep harmlessly through the inner layer while the hard outer shell held the pressure. Genius born from disaster. And the catalyst problem was even harder. Finding the right catalyst took years of grinding, obsessive work. Haber and his team tested over 10,000 different materials before they found one that actually worked. The winner was iron, mixed with traces of potassium and aluminum oxide. Simple, cheap, and devastatingly effective. The Haber-Bosch process was finally ready. By 1913, the plant at Oppau was producing tens of thousands of tons of ammonia per year. Fields across Germany were flooding with cheap nitrogen fertilizer. It looked like pure triumph. Then, in the summer of 1914, everything changed. A single assassination in Sarajevo lit the fuse, and Europe exploded into the largest war the world had ever seen. Britain's Royal Navy immediately blockaded Germany, cutting off all sea trade. Among the things that stopped coming was Chilean saltpeter, the nitrates Germany needed to make gunpowder. Military planners calculated Germany had maybe 6 months of nitrate reserves. Without a solution, the guns would go silent by 1915 and Germany would lose the war by default. But ammonia can be converted into nitric acid, and nitric acid makes explosives. The Haber-Bosch process was not just a fertilizer machine. It was an ammunition machine. Fritz Haber did not hesitate. He was a fierce German patriot, and he threw himself into the war effort completely, redirecting his entire institute toward military chemistry. The same genius that had learned to pull nitrogen from the sky was now being aimed directly at the battlefield. The process that fed the world was about to help destroy it. The war had been grinding for 9 months. Trenches stretched from the English Channel to Switzerland, and neither side could break through. Fritz Haber had a plan to end the stalemate, not with bullets or bombs, but with chemistry itself. 6,000 steel cylinders were buried along a 4-mile stretch of the German front near Ypres, each one packed with liquid chlorine under pressure. Haber stood on the front line in his military uniform, smoking a cigar, waiting for the wind to shift. He had studied the weather reports for weeks. At 5 inches the evening, on the 22nd of April 1915, the wind finally turned toward the Allied lines. The order was given. A yellowish-green cloud began to rise from the ground and drift slowly across no man's land. It smelled of pineapple and pepper. It was twice as heavy as air. Allied soldiers saw the cloud coming and had no idea what it was. Some thought it was a smokescreen. Then it hit them. Within minutes, 1,000 men were dead. 4,000 more were injured, choking on their own destroyed lung tissue. It was the first weapon of mass destruction ever used in battle. Haber returned to Berlin a hero. The Kaiser's government celebrated him. He was promoted to captain on the spot. 5 days later, his wife Clara walked into their garden in the middle of the night. She took his service pistol and shot herself. She was 45 years old. Haber left for the Eastern Front the next morning. The man who had fed the world had crossed a line that could never be uncrossed. Haber returned from Ypres, not haunted but energized. He had proven his theory. gas could win the war. Within months, he was appointed head of Germany's entire chemical warfare service. A scientist now commanded an army of chemists. Chlorine was only the beginning. Haber's teams began testing phosgene, a colorless gas that smelled faintly of cut hay and killed with terrifying efficiency. Phosgene was responsible for nearly 80% of all gas deaths in the war. Soldiers often felt fine for a day before their lungs simply filled with fluid and they drowned. But Haber kept pushing. In 1917, his teams unleashed mustard gas, a blistering agent that didn't kill quickly. It maimed, blinded, and consumed soldiers over days. The Allies retaliated with their own chemical programs. Both sides poured resources into gas development, turning chemistry into a new kind of arms race. Gas masks improved rapidly. Haber's response was methodical. He formulated new compounds specifically designed to defeat each new filter the Allies developed. From this obsession came Haber's rule, a cold equation stating that concentration multiplied by time equals a lethal dose. Gas death reduced to mathematics. When Germany surrendered in 1918, the Allies published a war crimes list. Haber's name was near the top. He fled to Switzerland and waited. Then the Nobel Committee made its announcement. Fritz Haber, still on a war criminals list, had been awarded the 1918 Nobel Prize in Chemistry for the ammonia synthesis process. The Nobel Prize announcement landed like a grenade. Scientists across Europe were furious, calling Haber a war criminal who poisoned thousands. Haber accepted the prize in Stockholm, composed and dignified. He genuinely believed his work had saved more lives than it had taken. Back in Berlin, Haber returned to his institute with renewed energy. The war was over. Now he would use chemistry to build, not destroy. His institute became one of the most respected scientific institutions in the world. And in the early 1920s, one of its projects was developing a powerful new pesticide. They called it Zyklon A. It was a hydrogen cyanide compound designed to kill insects in grain stores and ship cargo holds. Haber died in 1934, before he could see what his research would become. He never knew what Zyklon A was about to evolve into. After his death, chemists modified the formula. They removed the warning odor. They stabilized it into pellets. They called it Zyklon B. The Nazis used Zyklon B in Auschwitz and other death camps to murder over 1 million people. Among them were Haber's own nieces, grandnephews, and family friends. Haber had converted from Judaism, served Germany with total devotion, and called himself German above all else. In 1933, the Nazis expelled him simply for being Jewish. He wandered Europe for months, looking for a laboratory that would take him in, a country that would call him its own. None truly did. He died in a Basel hotel room, alone, in January 1934. Haber died alone, stripped of everything he had given his life to build, but the process that bore his name did not die with him. By the mid-20th century, the Haber-Bosch process had spread across every continent. Factories the size of small cities were pulling nitrogen straight out of the air and pumping it into the ground. Today, the process produces 170 million metric tons of ammonia every single year. To put that in scale, that is more than 20 kilograms for every person on Earth. Running all of that machinery burns roughly 1 to 2% of all the energy humans consume on the entire planet. It pumps out nearly 1 to 2% of all human carbon dioxide emissions. But the carbon footprint is almost a distraction. The quieter catastrophe is what happens after the fertilizer hits the soil, and then the rain comes. Rain washes excess nitrogen off fields and into streams, rivers, and eventually the ocean. When nitrogen floods a body of water, something alarming happens almost immediately. Algae explode. Billions of tiny organisms bloom so densely they turn the water green, then brown, then a thick, toxic soup. Scientists call it eutrophication. When the algae die, bacteria decompose them. That decomposition consumes every last molecule of oxygen in the water. Fish, crabs, shrimp, everything suffocates. These are called dead zones. In the 1960s, scientists had identified 9 of them on Earth. Today, there are more than 500. And there is a second invisible disaster happening in the soil itself. Bacteria in the ground convert excess nitrogen fertilizer into nitrous oxide, a gas that escapes silently into the atmosphere. Nitrous oxide is roughly 270 times more potent as a greenhouse gas than carbon dioxide. One man found a way to feed the world and quietly handed it 2 of its worst crises. So here we are, 1 molecule, 2 destinies. The same nitrogen atom that ripened wheat in Kansas also drifted as poison gas over Ypres. Fritz Haber made that split happen. He did not stumble into history. He chose his direction at nearly every fork in the road. Think about what he pulled off in that Karlsruhe laboratory in 1909. He held nitrogen gas and hydrogen gas under extreme pressure and coaxed them to bond. No living thing had ever done it that way. Before that moment, every nitrogen atom in every human body had passed through soil bacteria or lightning strikes. Haber rerouted nature herself. Roughly 4 in every 10 nitrogen atoms inside a human body today pass through an industrial reactor first. Billions of people are walking proof of what he built. And yet, the same genius organized the chlorine attack at Ypres in April 1915. His wife Clara begged him to stop. He left for the front the morning after she took her own life. He won the Nobel Prize in 1918, while the world was still counting its dead. The committee gave it to him for feeding humanity. History refused to let him forget the other half of the ledger. Then the cruelest twist. The Nazis stripped him of everything in 1933 because he was Jewish. The country he had gassed for, starved for, bled for, threw him out. And the pesticide chemistry his institute pioneered later became Zyklon B, the poison that murdered his own people in Nazi death camps. His science outlived his exile and turned against his family. He died alone in a Basel hotel room in January 1934. Somewhere between a genius, a patriot, a war criminal, and a man history could never quite file away neatly. The ammonia molecule did not stop moving after he died. Today, it sits at the center of the next great chemistry problem. Can we make it without fossil fuels? Green ammonia, powered by renewable electricity, could feed the world without drowning the oceans or heating the sky. The molecule that broke the planet may also help fix it. If this story made you think differently about the chemistry running your world, subscribe and watch the gasoline video next. The molecule in your fuel tank has a story just as wild.